Okay, I don't know why I missed these two slides last time. They were in one part of my notes, but not in my other. This is a map. Oh, I can go to full screen. This is a map of seamounts, and you can see that they're restricted kind of in location. Anthony's still here. They're not all over the world. In fact, I can do it with this. Where's my cursor? My computer, my cursor. These right here, they're called the Emperor Seamounts, and they're really important because the Kuroshio current actually interacts with them. Yeah, but they are actually the tail end of the Hawaiian Islands. So the hot spot that has given rise to the Hawaiian Islands actually started up there and then kept moving to the southeast and is still going. So all this lava stuff that you see is it's still happening. So these are all the seamounts are volcanic in origin, and so you can see there is a plate. There's a plate boundary right there, and so all of these are volcanism that's activated by the plate. And this is, if you've ever watched shows about life in the deep ocean, the hot vents, a lot of them happen right along here. And so, you know, they've studied these animals that do not, they don't breathe oxygen, they actually breathe sulfur. And I don't know why I missed this one. This is a kind of a cool picture of a seamount and a guyot. The guyot are the flat top ones. And the flat top means that it was once upon a time above the ocean and has sunk below the ocean. So I missed that. I don't know why I missed that. Now this next part, you guys should be very sensitive to. We're going to talk about sea level rise. And there's, there's a number of things that cause sea level rise. Well, there's really only three things. You change the basin, and so you don't think about it, but I told you about these atolls. If they erode, that comes out like a sea level rise because they're lower. They're flat to begin with, so there's not much. You change the basin, or you change the amount of water in the basin. So that would happen primarily by the melting of land ice, of glaciers, ice sheets. And the third thing is to raise the temperature of the ocean. So you expand the water. So there have been decade-long events where sea level has risen and then subsided again and then risen again. But there has been now this continual rise, and this is one of, I think Niram created this one, I'm not sure. It's part of the Topex Poseidon thing. One of the places that, and I'm showing you all these slides because I had this neat movie of this Jakobshavn's glaciers melting, but you know how all these operating systems upgrade themselves? Nothing will play it anymore. So it's something I've had it for, tens of years, I guess. So I just pulled a bunch of other stuff. So this is this glacier right here, and it's really dramatically melting and putting fresh water into the ocean. So this, it's not real easy to see, but this is the seaward side where it breaks up and forms little bergs and little bergy bits. And then this is the calving boundary, and you can see, this is where it was in 1800 and 60, 51. Anyway, so these are the 1800s, and we're up now. This goes to 14. So we're way up here, and that's really a dramatic change. And the calving front, here's a picture of how when it breaks off, then all this other stuff turns into little bergs and bergy bits. And this is an illustration of how this stuff flows down, and I'll show you some real pictures of it because it's really very narrow if you look at the aspect ratio of that channel. So this is kind of a... Does anybody watch the calving of icebergs? Yeah, it's cool, right? You know, they're all breaking off. It's different in the Antarctic. In Antarctic, they don't do it. These are, in the Arctic, you get these steep pinnacle bergs, and we're going to talk about that later. But in the Antarctic, it just breaks off a piece of sea ice, and it forms these big tabular bergs. So in the Arctic, you get these steep pinnacle bergs. But in the Antarctic, they're flat, big tabular bergs. I like this illustration. So it shows you in 100 years, it went from the 1902 to the 2001 in 100 years. And then it went from this 2001 to the 2010 in 10 years. So it's really accelerated its melt. And this is just kind of a cool picture. People actually live up there. So this is one of the settlements on the tip of Greenland. And this is showing you the calving front in the glacier. One of the interesting things is while the boundaries are melting and losing, the central part of the ice sheet is actually accreting. It's gaining. It's getting thicker. I don't believe it's offsetting what's being lost, but it is getting thicker in the middle. So this shows you a number of the glaciers that are losing the ice. This is one of the main ones. Does anybody know what Thule is?
Air Force Base.
It's an Air Force Base. It's a U.S. Air Force Base. And what's this over here?
Iceland.
It's Iceland, yeah. So Greenland is not green. It's plain white. And Iceland is not frozen. I've been there a couple of times. A friend of mine is the president of the University of Iceland. So this shows you this glacier coming down and shows you how all of the ice feeds in. And one of my former PhD students, he went up there and they were going to fly UAVs to measure the melt ponds. And every time they'd get out there, the melt ponds had drained. So, melt ponds happen when you get enough solar insolation and they form these melt ponds. But then if you get a little bit of leakage underneath, boom, the water all goes out. So this shows that the center part is accreting, and this shows the 2,000 meter elevation, that little line here. This one shows you how narrow it is I showed you how wide it was here, but that's getting close. This is a big close-up. If you back off and you look at the topography, it really is, in terms of its aspect ratio, very narrow. It's a narrow flow into it. This is looking down it. Okay, this is the Antarctic Peninsula, and this is a multi-year ice shelf that's been disintegrating. This is the ice cliff, and so the Antarctic's really interesting. We have a whole section on the Antarctic. It has mostly first-year ice. It has two kind of limited ice shelves, but most of the ice in the Antarctic is first-year ice. It melts and freezes every year. It's a tremendous amount of energy involved. I mean, you're talking about a huge amount of energy. I like this. Anybody been skiing on Mount Hood? It's not bad. It's not good up here, but it's typical West Coast kind of skiing. It's really wet stuff. That's 1984, August, and this is late summer 2002. Big difference. This shows you the Antarctic Ice Shelf. So we really only have this one on the Ross Sea in here. There's a little teeny one over here. And this really isn't an ice shelf. But this is a really interesting area because when we talk about water masses, you're going to find out that most of the bottom water in all of the ocean comes from here. And this is one that shows you that it's, you know, decreasing on the edges and increasing in the middle. This next one is, is it my last sabbatical? Yeah. And the last sabbatical in Germany, everybody was really worried about this. A friend of mine, he studied cyclonic circulations. They're kind of, does everybody know what a Taylor column is? Taylor column is something that rotates from top to bottom. It's a mathematical solution. Well, they had these chimneys, if you call them that they could measure. They were eddies in east of Greenland. And everybody figured that because a cyclonic cell will bring stuff up from underneath. We'll talk about that when we talk about the dynamics. And so that was a reason that you would have colder water and the Gulf Stream would come and melt the colder water. So everybody, this guy then found that there were fewer and fewer of these chimneys. You know, he'd go out the next year and didn't see as many as he'd seen the year before, and he started to scare that the Gulf Stream would not be going in its normal path. Well, when we talk about the Gulf Stream, you'll see that, you know, after it leaves the coast for a ways, it's all tentacles. But his thesis was that it would not be bringing as much warm water. It would change the climate of the UK, of Western Europe. They would be getting much worse storms. They would get more snow and ice. It's really it's a doom and gloom kind of thing. It really didn't happen. But and the poor guy was really ignored after that. Nice guy, Peter Wadham's a friend of mine, but it was a little bit, you know, a little bit scared tactics. This is kind of interesting. This is the number of days greater than or equal to 90 degrees Fahrenheit and 95 degrees Fahrenheit. So, you know, the short bar is the earlier one and the next one later, so the baseline, and then there's after it. And so it's getting more. But mind you, there's still decadal changes. Did I ever tell you my position on global warming? I get asked it a lot. I said, well, what's the main greenhouse gas? What's the main greenhouse gas? What do you think? What?
Well, CO2.
CO2? I heard another word. Who said water?
Yeah.
Water vapor is the main greenhouse. That's the main, and if it wasn't for water vapor in the atmosphere, we couldn't live here. This would be an ice cold rock. But we have water vapor. But water vapor is in equilibrium, so you don't worry. But that means the greenhouse is an absolute fact. It happens, right? It works. Are we putting more junk into the atmosphere? CO2, methane, whatever you want to call it. We're putting a lot more. And, you know, they've been measuring on Mauna Loa, where my house is, up on the top, though. They've been measuring it since 1957, and it's going up and up and up and up. Do I know what's going to happen? No. And anybody, regardless of their scientific field, that tells you they absolutely know what's going to happen is lying. They don't. Okay? I mean, you know, the modelers, they have to kick their modelers with huge increases to make it do anything. But I know one positive thing, one absolute thing. If they don't give us scientists more money, we'll never figure it out. That's true. It's kind of, you know, facetious, but that's where it's at. This is kind of interesting. This is a little island in Chesapeake Bay that in the 40s looked like that, and in the 80s, I would suspect now it's virtually gone. This is sea level rise measured from cores and land measurements. So it's been going on for a long time. It's not just now. It's not since the advent of altimetry that sea level rise has occurred. It's been going on for a long time. And these are the kinds of things that Gore showed in his movie, the places that would be wiped out with a moderate sea level rise. I mean, he showed the Manhattan one where, you know, most of Manhattan's flooded. And here the Keys are all gone and Miami Beach is wiped out. So there are other things that cause sea level rise. This is a sea level rise that has nothing to do with melting sea ice or warming of the oceans. This just talks about changes in the climate that will change you know, the way the waves and the build up on the shore. So there are other things that can change it. Okay, sill. So a sill is something that is a ridge, right? A sill usually is something that is at the boundary of some sort of marginal sea. So one of the best ones, for example, there's a sill in the Mediterranean. It's much shallower than any of the rest of the Mediterranean, and it's certainly a lot shallower than the Atlantic. And so it's the sill depth, and that sill depth then is very important for how the basins communicate. So we'll talk about that when we get to the Mediterranean. Bottom material, I think I've talked to you about this. The deep, now that I think we've got, I thought Kandala would be here by now. She's not. I had this idea. See what you guys think. For a midterm, have you guys write some questions. I can't, this class is too small, I can't turn the class around, besides that, drive him crazy with all his cameras and stuff. So, I'd have you guys write questions and answers. And then we'd put them together and we'd have a test. Whatever. How's that sound? It beats,
Yeah, right?
I can always gen up stuff, but it turns out to be the same old stuff since I've been teaching this stuff. I've been teaching, how long? I've been teaching this stuff for 45 years, so. Yeah, I'm thinking about it. So that's kind of an idea. Okay, two major deep ocean sediments are red clay and biogenic oozes. This is really ushy-gushy mud. I'll tell you, squishy, fishy stuff. I've seen it when they bring up dredges. So the red clay has only 30% biogenic material. What does biogenic mean? That means it's the bodies of dead animals or plants. So everybody knows the difference between phytoplankton and zooplankton. Phytoplankton are the plants in the ocean, and the zooplankton are the animals. And these guys are all, they're things you have to look at with a microscope. They're not the fish. And so the red clay has a lot of stuff from the land, and a lot of it has carried by the air and then dropped. Some of it has been entered into the ocean. There's volcanic material and meteors if they fall in the ocean. The oozes are more than 30% biogenic. They're mostly stuff from the dead animals. There's a thing called a calcareous ooze. So they have a high percentage of calcium carbonate, because a lot of the critters have calcium carbonate bodies. So that's mostly plankton. The siliceous oozes have a lot of silica from plankton, from phytoplankton. So the distribution of these calcareous and siliceous oozes is related to the nutrient content and how much that kind of productivity is. Oh, I'm going to give you all of these slides. I haven't set up D2L yet. I mean, this house thing has been driving me crazy. But when I get it set up, I'll put all of the slides out on D2L. So don't feel like you have to furiously scribble everything down. If you want to put down something to remember, that's great. But I will give it to you. So the average rate of deposition of the sediments is from a tenth to 10 millimeters per 1,000 years. So it's very slow. But it's had a long time to do that. So samples of the bottom material, you do it with a core, which is a steel pipe that you put down. So they represent material deposited over a period from 1,000 to 10 million years per meter of length. So this stuff has just been gathering down there. There's not a lot of motion down there. Sediments can affect the properties of seawater that's in contact with them. And organic carbon, which is from fecal pellets. What are fecal pellets? Poop. This is little, microscopic things got to poop. So that's what they do. And it gets decomposed, so it's remineralized, it's oxidized into inorganic carbon dioxide. So the thing that's important about that is this oxidization process takes place as the dead critters die and then are falling through the water column. So their bodies are being oxidized, and that uses up oxygen in the water. Carbon dioxide-rich, oxygen-poor waters in the sediment can be released back into the water. Okay, nitrogen, phosphorus are also remineralized, and regions where all oxygen is consumed, methane forms from bacterial action. So bacteria can produce the methane. And this methane is often stored in a solid form called the methane hydrate. And I don't know, have you guys ever heard about these giant bubbles that come up from the ocean? They're full of methane. They're just nothing but methane. Huge bubbles that come up. That's from these methane hydrate deposits. So vast quantities, 10 to the 19th grams. Maybe I ought to turn that into something. Well, that's a lot of kilograms. Methane hydrate have accumulated in marine sediments over Earth's history. So there's a lot of that stuff out there. And they can spontaneously turn from solid into gaseous form, causing submarine landslides and releasing methane into the water. These are the big bubbles. Okay, that's so much for that one. Okay, so that's it for talking about the basins. Yeah, this is the boat I went on. Okay. Okay, next we're going to start talking about the water itself. And water is really interesting stuff. We all know that, life can't exist without it. Water is a polar molecule. So it has a couple of H's on one side, and it has negative O2 on the other side. So it has a polar orientation.
Shouldn't that just be an O?
What's that?
Shouldn't it just be an O? Not an O2?
Just be, no, yeah, it should just be an O. It's H2O, right?
Yeah.
You're right, absolutely right. And you'll see it, yeah, that's an O. But O is still the negative.
Yeah.
So take the 2 off of there. I should take it off of there. That's not an O2. What?
It's -2 charge, right?
Yeah, O2 minus.
Yes, that's probably what I'm trying to show there. So this polar arrangement gives it all kinds of interesting characteristics. One is it forms chains. And I used to tell my chemistry friends these are polymers. They said, no. Only organic molecules form polymers. These are chains. But they're chains, so, the negative hooks up with the positive, hooks up with the negative, up to like eight molecules. And the chains are really important because the chains, contain energy. This molecular polarity, it leads to the water having a very high dielectric constant, which is the ability to withstand an electric field. It leads to the property that water is able to dissolve more substances than any other fluid. And you guys know this, right? I mean, we've learned it from when we were little kids. You mix everything with water, right? You want to make, even now we have latex paints, which is everything's diluted with water. So water is the best of any fluid to do that. And that's because you end up with the water molecules can shield the other one. You get the positives glued onto one part and the negatives glued onto the other parts. So this is why the ocean is salty, because it takes a sodium and NaCl, which is salt, breaks off the chlorine, gets the sodium, and they both get insulated. Now you have salty water, but it's not salt. It's salty water. So these chains, up to 8 molecules, takes a certain amount of energy, goes into linking the molecules. So this explains the ocean's ability to absorb and retain heat. So without the chains, it wouldn't be as good as it is for retaining heat. And that's extremely important for the world's climate. This is the reason that the ocean plays such an important role in the climate. So the molecular chains occur for about 90% of the water molecules. As a consequence, water has the highest heat capacity of all liquids except ammonia. And I'm glad the ocean isn't ammonia, because it would really be awful. So this is the energy that goes into this heat capacity, into the chain formation. So this shows you a fraction of molecular chains, aggregates, as functions of temperature. Okay, and what you're going to find is the two processes, we're going to look at it, if you contrast breaking down the chains and thermal expansion, water ends up having a maximum density at 4 degrees C. So unlike land, the land doesn't store heat very well at all. It's actually a great insulator. I mean, when we lived in Australia, I had funds to tour around, give talks about remote sensing. So we drove right up the middle. And we had to stop at Coober Pedy. Has anybody ever heard of Coober Pedy? It's where 90% of the world's opals come from. And it's in the middle of the outback. I mean, this is a proverbial middle of nowhere. Really, really hot. But the miners learned that the most comfortable place was down in their mines. The land just totally inside. I mean, it can be 120, 30 degrees outside. Inside the mine, it's 70 degrees. So you stay in the underground motels. It's really great, Everything, all the wiring and stuff are right on the side, and you're in basically this cave. The only real light you would get would be from the front door. And it was great. My wife has rheumatoid arthritis, and she had to go to her arthritis doctor in Hobart, where we lived. And she told him that we were going to Coober Pedy, and he said, "Oh, it's a horrible place." He said, "If God was going to give the earth an enema, that's where he'd stick it." We had a great time. We thought it was a wonderful place. It was really unique. The heat that's absorbed by the ocean is carried by the currents, exporting it to various regions. And that's why a lot of places have climates that they wouldn't have otherwise. So if you think about the climate of Washington State and British Columbia compared to the East Coast at that same latitude, totally different climates. If you think of the UK versus Siberia, which is sort of the same latitude, totally different climates. And that's because of the presence of the ocean bringing this heat. So as the water is heated, molecular activity increases, it expands, that reduces the density, right? But at the same time, the chains break down. Okay? So as the chain breaks down, the density gets less. The thermal wait a minute, is this going the right way? Yeah. So the crossing point is right at 4 degrees C. Okay, and that's a maximum density due only to this trade-off between chain breakdown and thermal expansion. So this is showing you the dissolution of salt. So there's a sodium guy and a chlorine guy, and they're all protected by the little water molecules. This is an interesting plot. This is a plot that oceanographers use a lot, temperature versus salinity. Those are two variables that can be observed, and they basically dictate the density. That little dark bar is 90% of the world's ocean. So they're in a really restricted little range down there. Important to note on this diagram, where is my cursor? There's a crossing point here too, the temperature of maximum density and the freezing point. So it's going to be important when we come look at areas where water freezes, okay? Because if it had to keep turning over, you know, you'd never really freeze the ocean because it's deep enough. But it doesn't, it only has to really end up freezing the surface. This is one you probably don't think about. Water has the highest heat of evaporation or heat of vaporization of all substances. So I like this plot. We don't think about this very much. But this is temperature on this side and the heat change per unit mass. So you heat it up, and it goes through, so we're in an ice stage, and we heat it up, and we go into a liquid stage. So that's a phase change. There's no temperature change because we're changing phase. And then we heat up the liquid, and then there's a much longer phase change to get it to a vapor. So this has gone all the way from ice to a vapor. And it has the highest heat of vaporization of any substance. Okay, I talked about this last time. Another important effect of the chains in the molecular structure is the fact that that gives water a high surface tension. And it's this surface tension that is actually the source of the momentum transfer from the atmosphere to the ocean. It's this forms what are known as capillary waves, and the capillary waves are taking energy from the atmosphere and putting it directly into the ocean. So these capillary waves are little teeny waves that happen when the wind blows, and they're very important in determining the friction between the wind and the water, which has been a subject of a lot of study and debate over the years. But I think we've got it pretty well figured out now. Okay, so that's water. Not ocean water, that's just water. We're just talking about water. Very, very interesting stuff. Okay, now we're going to talk about seawater. Where does the salt for the ocean come from? Where does it come from? The ocean's salty.
Is it the rocks or something? Minerals, like on the bottom of the ocean?
On the bottom of the ocean? Some of the early oceanographers, even up into the 1800s, were still thinking there were fountains of salt in the bottom of the ocean. There aren't any. So where does it come from? It comes from the land. It comes from the rivers. Somebody said that, was it Aristotle or Socrates? I can't remember, one of them, threw himself in the ocean and drowned because he couldn't explain the fact that the ocean was salty. And rivers were fresh. But turns out those fresh rivers are dragging all the stuff down into the ocean. It accumulates there, and it's salty. And that's where it comes from. It all comes from the land. It's all in the chain. And that's why I told you early on, in the final analysis, the ocean is the world's sewer. Everything will eventually end up in the ocean. So, temperature is probably the most important oceanographic variable, and it's the most widely observed variable historically. Salinity is the next most important. Temperature is the primary parameter determining things like sound speed, which is very important if you're a submarine or a destroyer or whatever looking to find submarines. Most of the ocean, the salinity variations are not very great. There are a few exceptions to that. Places like the Red Sea and the Mediterranean, and there are kind of large changes. Changes in salinity turn out to be important in some places, but not everywhere. Temperature is the primary driving force. Temperature is defined by its relation to heat content. Okay, so we just said water has this ability to carry heat much more, or to absorb and retain and carry the heat more than the atmosphere. The atmosphere does not have a really great ability to carry heat. The ocean does. And we're going to end up talking about a concept called potential temperature, which I'm sure you've never heard of. But that takes the pressure effect into account. Because if you try to measure temperature, temperature is really a measure of molecular activity. And if you go down to the bottom, well, the molecular activity is restricted not only by the actual temperature, but by the physical constriction. The pressure is now, pressure down to 5,000 meters is a lot more than here at the surface. So temperature is a thermodynamic property. Heat and temperature are related through a thing called the specific heat, which is a constant. When the heat content is zero, temperature is also absolute zero, which we've never achieved, although guys here in Boulder got pretty darn close. We're going to use the Celsius scale. Kelvin is what you use if you're dealing with absolute temperatures. The nice thing about Celsius is 1 degree C is the same as 1 Kelvin in terms of the temperature chain. 0 C is 273.16 Kelvin. A range of temperatures in the oceans from the freezing point, which is about minus 1.7, to a maximum of about 31 degrees C in the tropical oceans. I've actually seen 32 in some cases, but it's pretty rare. The range is considerably smaller than the range of air temperatures. And that's, again, this chain stuff, keeping everything without a lot of changes. Temperature, the question? Temperature scale was defined by an international agreement. In 1968, they had the International Practical Temperature Scale. And it's been superseded by the 1990 International Temperature Scale. There's one thing that everybody can agree on. This is called the triple point of water. And it is essentially a point at where the water, this is used to calibrate. This is a very convenient way to calibrate. Okay, so this is where, you know, you essentially have this is the change in that phase that we looked at. So when it's at one of these phase changes, everybody knows what the temperature has to be. So the International Temperature Scale of 1990, well, we all know that. We all know that. We all know this. So this is just the definition of what they came up with. Want to talk about how oceanographers measure temperature. When we talked about the Challenger expedition, they didn't have any way of measuring the temperature at the bottom, so they used what were called min-max thermometers. It could measure the minimum temperature and the maximum temperature, but you couldn't tell for sure where that occurred. So everybody wanted to be able to trap the temperature. So some really clever guys, and these guys, Negretti and Zambra, does that sound like Englishmen to you? These guys were in England. They developed this in England. So they invented the reversing thermometer. And I know that they actually existed because I was eating at a McDonald's. Yeah, I do eat at McDonald's once in a while. I was eating at a McDonald's in Vancouver in West Van, and you know how they have the tables are, you know, old newspapers and stuff. And this was an old UK newspaper, and there was an ad for reversing thermometers by Negretti and Zambra. It was a for real ad. What? Probably the only person in the whole restaurant knew what the heck that was. This was ingenious, it says, ingenious glasswork. Mercury, you know, and that's another thing. You know, when we were kids, we played with mercury all the time. You know, we took it to school and banged it around the desk. You know, now it's deadly poisonous. Stay away from the mercury. You know, but these guys realized that mercury would break in a predictable place if it was neck down. If you know, so they built these thermometers. And they had this thing where the mercury would always break there. Okay? So what they would do is this thermometer had these, was called the pigtail appendix, because it looked cut like a pig's tail, you know, curly. And when it would be reading, it was actually upside down. So this is the reservoir there. So when you really put it in the bottle, you put it in this way. Okay? What it would do, and then you would send these messengers down, and they would hit the bottle, and the bottle would flip over, which would flip over the thermometer, breaking the mercury at that spot, trapping the mercury as it read at that depth. So we actually trapped the the temperature measurement. Now, what?
Is it a single use? They use the same one again?
Oh yeah, no, you could use these again and again. Yeah, they went in the bottles. In fact, I had this funny experience. I was the chief U.S. scientist on a Russian expedition to the Antarctic. I went to the Antarctic with the Russians and with the Americans. And I brought these reversing thermometers from Scripps that we borrowed from Scripps, and we were supposed to do an intercalibration between their thermometers and our thermometers. And the guy that was in charge of the hydrographic stuff, he said, what are they worth? Well, the thermometers don't cost very much. The thermometers cost a few $100s. But the calibration also costs a few $100s. And these things have been calibrated many times. So they're worth probably thousands of dollars by then. And he said, well, we don't trust our bottles to stay on the line enough. We won't put them in there. Besides, they were too long for their racks. And their thermometers were horrible. You have to design your thermometer very carefully. It has to have a very straight capillary, or you won't get a good reading. The Russian ones looked like a washboard. I mean, they were terrible. And they knew they were terrible. Anyway, you'll see 2 thermometers in there. There's 2 thermometers in there. And so when this thing was brought up to the surface, well, you had that mercury trapped, but now it's going to warm up, right? And so you have an auxiliary thermometer, a regular thermometer in there, and you had to correct the expansion of that mercury for the temperature when you read the temperature of the mercury. So it was a really involved process. You had to read each thermometer, and it's the usual reading thermometers, there's gradation here, gradation, and then you guess at the last one. You just totally guess. Interpolation. I don't know why, I taught undergraduates, they didn't know how to interpolate. I thought it was human nature, you know how to interpolate. But they didn't. So you had to read each thermometer twice by 2 different guys. And you wrote all this stuff down. And then you had to average all that stuff up. So you're trying to beat down human error. Anyway, that was a reversing thermometer. And it was a huge, tremendous development. So it made it possible to actually measure the temperature at depth. So the accuracy and precision of reversing thermometers, 0.004 and 0.002. So it fairly precise. I mean, we've got a little better now. We're up to 0.005, so another digit, but it's pretty good measurement actually. And the interesting thing was people realized that the difference, there were 2 kinds of thermometers. One was called protected, so it's completely encased in glass. And one was called unprotected, so you can see it's open at the top. And they realized that if you did that, the difference between the protected and the unprotected was a measure of the depth. Because the bottles don't ever really, you can tell the amount of wire that's out, but the things are floating out here. They're not hanging straight down. So you wanted a way to estimate the correct depth, and that would give you a measure of the depth. So it was a real development. They were really pretty accurate. Satellites, we can't do anything close to that kind of accuracy, but we'll talk more about satellites later. People used to correct satellites with ship measurements, but that really changed. We'll talk about sea surface temperature later. Okay, so this is okay. Heat. There's an interesting story. I told you about the meteor, you know, they did all these sections across the Atlantic by this guy, Garrick Boost, the guy with the pith helmet, who was my advisor's advisor. He spent a couple of years at Lamont in New York, and he wrote this paper about the fluxes of all of these quantities in the Atlantic Ocean, north-south fluxes. And he left out heat. Now, heat's the easiest one, right? All you do is you take all the temperatures and you add them up, and that's heat. He left it out. Well, Hank Stummel, who was a very famous oceanographer, is no longer with us. He suspected that Voost actually got the right answer because, you know, your intuition would say the heat should flow from the equator to the poles, right? Well, in the South Atlantic, it doesn't. It actually flows to the equator. And he figures Voost got the right answer, but didn't believe it, didn't trust it. So Stummel, being this usual careful guy, he traced down one of Voost's old graduate students, who was an admiral now in NATO, and I have a copy of the letter. And the guy wrote back, he says, yes, Professor Voost found that the heat flew in the wrong direction, and he wouldn't put it in the paper. So you gotta watch, you know, it's the old throw the baby out with the bathwater kind of idea. Your prejudice might not be right. You know, your results might be better than your prejudice. Okay, specific heat actually depends on both temperature, pressure, and salinity. But so this is how you calculate heat: rho, specific heat, temperature. And I'm not going to belabor you guys about the equivalence between heat and energy. But we are going to talk about potential temperature. So this is Physical Oceanography Confessions. Physical oceanographers are going to consider the ocean compressible and incompressible. So they're going to consider it incompressible when it's convenient, and they're going to consider it compressible when it isn't. They're guilty. Potential temperature is an admission that the ocean really isn't incompressible. It's close, but it's not. So there's compression that causes the temperature in a water parcel to go up. If you could, you know, if you had one of those transporters like they do on Star Trek, and you could take a water parcel and take it from the surface down to 5,000 meters, and it's adiabatic, you don't change any heat, its temperature would be higher. So that means that if you measure temperature down there, the temperature really doesn't represent the heat down there because it's got this pressure effect. So you have to take the pressure effect off, and that's potential temperature. So it's defined as the temperature that a water parcel would have if it moved adiabatically to another pressure level, basically to the surface. We're going to talk about other levels, but mainly to the surface. So if you took that parcel, raised it up to the surface, it's going to have very different temperature than what you would have measured down at the bottom. But you want to correct that for that effect. So there's a thing called the adiabatic lapse rate. That's really the temperature gradient. Lapse rate, we take that from the atmosphere. That's what the atmospheric guys talk about, lapse rates. Okay, there is a formula for this potential temperature, but I'm going to give you a homework problem and I'm going to give you a table that you'll have to interpolate, but you can figure out the corrections for, it's data from the Marianas Trench. I think that's right. It's a trench. It goes really deep. So, for example, if you had water of a temperature of 5 degrees C and a salinity of 35, PSU means practical salinity units, but it actually turns out to be the same as parts per thousand. Oceanographers that as old as I am learned parts per thousand. They brought in practical salinity units later. Parts per thousand is written, instead of percent, it has 2 O's on the bottom. So it's not percent, it's parts per thousand. If you had that and you lowered it adiabatically from the surface to a depth of 4,000 meters, the temperature would increase to 5.45 degrees C, strictly due to compression. So the potential temperature relative to the surface is always, so what you would measure in situ would be the 5.45, but it should have been 5 degrees. Okay. Conversely, if you measured the temperature at 4,000 meters, it was 5 degrees, and raised it to the surface, it would really be 4.56. Okay. So the potential temperature, and it's, so I'll do a graphical example. Okay, so notice, though, in this graphical example, so this, and we've blown it up here because it doesn't really make a difference till you get at least below 1,000 meters. It doesn't really get accentuated till you get down here much deeper. So potential temperature we write with a theta, so it's a Greek version of T. So these are the two temperatures. Okay. So we're gonna, like I said, there's a homework problem where we actually give you some real data, and we actually ask you to calculate the potential temperature. Okay, seawater is a complicated solution. It's not just salt. So it's got 55% chlorine. It's got 30.7% sodium. It's got sulfate. It's got magnesium. It's got calcium. It's got a whole bunch of stuff. I mean, there's a lot more in there. In fact, there's even gold in the ocean. It's just so hard to get it out. It's not worth the effort. Way back when, 1884, there was this guy Dittmer that says he had 77 samples of seawater on the Challenger expedition. And he said, well, he was confirming an earlier hypothesis, and he had a law of constant proportion. So he said that these ratios are the same everywhere in the world. Well, he turned out to be completely wrong, but that's what he did. I told you the old philosophers said there was a salt fountain at the bottom of the ocean. Well, there isn't. Not there. And it's the material in the oceans running down the river, material in the rivers running into the ocean. There's a lot of differences in total concentrations of dissolved salts, have to do with evaporation and dilution, rain and river runoff. So we're going to talk more about that and how that influences coastal seas. But those are important processes. Okay, in the good old days, well, I don't know about the good old days. In the old days, salinity was originally defined as the mass in grams of solid material in a kilogram of seawater after evaporating the water away. Turns out to be an impossible measurement. So they ended up doing it, well, you had this chemically based definition way back in the 1800s. They eventually fell on this one, and you have to realize in those days they found salinity by titration, which is a horrible job, especially at sea with a ship going like that, trying to titrate. This was a relationship between salinity and chlorinity, because if you remember right, chlorinity is, well, where did I have the ratios? Has mostly chlorine in here. Oh, where? I thought I had one that showed. Where did it go? Here, no. Oh, here it is. Yeah, chlorine's most of it. So they came up with this relationship. Later on they realized this was a lousy way to do it. This didn't really work. So they realized that the thing, well, actually, and titration was a horrible way to measure. They realized that salinity really changed the electrical conductivity of the ocean. And so measuring conductivity, now it also depends on temperature, so you had to have temperature either measured or controlled. Those are the two things. But conductivity, that was the thing that you wanted. So that's when they developed this thing called the practical salinity units. Okay, and so that all of the measurements since they developed this have been based on conductivity. So whether you collect the sample and bring it in and measure it with what's called a salinometer at home, or whether you measure it with conductivity in the ocean, it's done with conductivity. Okay, so this electrical conductivity was introduced in the 1930s, but it didn't actually get to be common practice till actually the late 60s, early 70s. So, and it's interesting because when you, and we have a whole thing on instruments, but I can't take this class to sea. Like if we were at an oceanographic institution, we'd go out on a ship and get you seasick. Who gets seasick? What? You get seasick? Yeah. Oh boy, you wouldn't do well. You better stay on the land. Yeah. I don't get seasick, but I have watched a lot of people, even some of my heroes, get violently seasick. So I don't know. Maybe my stomach's always upset. I'm not sure, but anyway, when you collect these samples, let's say you're still using a sampling bottle, and you collect the little sample bottle, and you have to process it on shore. You have to have something to calibrate it against, and so they had to actually end up making up some standard solutions, and these standards, well, they were regionally made at Copenhagen, so we had this stuff called Copenhagen water, and they put them in glass ampules. It's a glass tube where they just extrude the ends so they seal them by the glass, and then you'd break off the end and you'd pour that in your salinometer and make sure the salinometer measured. And so all of these were set at where 30, no, what is it? Anyway, 35 parts per thousand, that's what they were set at. And and that's changed because they quit making it in Copenhagen. Then it was made in the UK at Wormley, but then Wormley moved, and so it didn't move, and then went to Woods Hole. It's now made in Woods Hole. So the accuracy of a salinity determined from conductivity is about 0.001 if the temperature is measured or controlled. So there are two kinds of bench salinometers. One measures the temperature, and the other one controls the temperature. So this is a major improvement over the accuracy of the titration method, which was about 0.02. So you can see it's a pretty big increase. Now, a funny story. This is on the Russian ship. Of course, we had bench salinometers, and we would get a sample bottle from the samples that they collected, and we would process it, and they were still titrating. And why they were this is 1977, and they were still titrating. I don't know why. Some Russian in their group didn't trust salinometer. I don't know. Anyway, their salinities were so wrong, they got the Antarctic circumpolar current going in the wrong direction. And we said, no, if you look at this, it doesn't do that. So, big change. This whole development of conductivity changed everything. So, this was all based on things that were agreed on. And this guy Lewis worked at the Institute of Ocean Sciences in Patricia Bay in British Columbia. So I was in Vancouver at the time. And I'd running out of time. So pairing then these conductivity sensors with thermistors made it possible to actually deploy an instrument in the ocean and measure it conductivity directly, so we can measure salinity. And there were some real big mistakes to begin with. Turns out, the early conductivity cells got fouled really easily. They were actually the right way to do it, but they got fouled. And so they ended up using an inductive salinometer, which didn't get fouled, but was much slower. And they were using thermistors that were relatively fast. So it turned out that you were getting the wrong measurement because the salinity was always behind the temperature. And so they were making the incorrect measurement. I think we'll come back here. I remembered it because my professor bought a thing called the it was called, what was it called? It was called an STD, salinity temperature depth, and it didn't work. I mean, it gave you the wrong answers. So later ones were called CTDs, conductivity temperature depth. So that was kind of how they rectified that problem. Okay, well, if you guys like that idea, that's kind of what I want to do. So I'll probably restrict it to this creative, innovative midterm, the 2 homework assignments, and the take-home final. Unless you guys want more tests. Okay. But I may end up, I thought about assigning you guys to do little reports on interesting stuff, because otherwise you just hear my stuff, and you might actually find some new stuff that I haven't seen. So when we get into like El Nino and that sort of thing. See you guys Thursday.